And that hard drive had been formatted. And I called up the bank. And they said, well, we had all of our ATMs upgraded, and we hired a company to do it. And the contract said that they had to sanitize the hard drives. So we'll need to check into this, and we'll get back to you. Well, they checked into it. That company nobody does their own work anymore. That company had hired a subcontractor. And the subcontractor had been told to clear the hard drives, but hadn't been told how. And so that subcontractor used the format command. The supermarket had a policy in place at the time that the hard drive left the supermarket to clear every hard drive. But they didn't audit. And it may be that the person who was implementing the policy didn't know the right way to do it. This California electronics manufacturer, again, they had a policy. They were aware of the problem, but the person doing it just not properly trained. And then sometimes the data custodians just didn't care, and this was largely organizations that had gone into bankruptcy, and they felt that they had no responsibility to the people whose information was on the hard drives. There was an internet software developer, and they were just happy that the reseller would come and pick up the computers for free. A computer magazine, they had layoffs, and they basically said, well, we don't have confidential information, and if people were storing their own personal stuff on their office computer, that's their own tough luck. Now, there is no regulation on resellers right now, but if we had regulations on resellers, that would actually solve this problem. In this country, you're not allowed to sell toxic materials unless you're regulated. You follow the rules, and there's certain people you sell it to, and you can't. It has to be in special kinds of containment. But we allow people to sell hard drives that might have toxic data on them, because we have no regulations requiring that the resellers assume some sort of responsibility. In 7 cases, I wasn't able to determine the cause whatsoever. The mail order pharmacy, they just refused to talk to me, and under my terms through the MIT office, if they didn't want to talk to me, I couldn't force them to talk to me. Primary school principal's office, it was 10 years ago, and the principal had left. I had all these letters to parents of behavior problem children. And all those children are like going to college right now or getting their first jobs. So regulation would have helped there too. One would hope. One would hope. Now, I did not check them out. Now, it's interesting that the techniques that I had developed for my study were really different than the techniques for today's computer forensic tools. Because today's computer forensic tools are based on the sort of one drive, one person, one report model. The drive is seized from a suspect's house, or it's seized in the part of an investigation, and there's this interactive user interface. You have an examiner, and they have hours and hours to look for the incriminating data. And here's an example of the in-case user interface, and it will allow you to drill down in a Microsoft PST document and recover email. And this is great if you want to prepare a report for a courtroom. But it doesn't work if you have hundreds of hard drives to analyze, and you simply want to find the ones that will be most likely to give you good information. What is good information? Right? So for me, good information is stuff that shouldn't have been released. But for you, good information might be something else. So another problem with today's tools is that there are other problems that I kept coming up with. Like, this drive might have been previously imaged. And when you start dealing with hundreds of drives, keeping track of them and keeping track of their serial numbers and their images becomes a major problem. Just figuring out where to start. The tools that are developed for criminal investigations just don't work for this kind of problem. So I'm going to give you an example of 2 approaches that I developed. The first approach is to look for Microsoft Word files and try to determine the owner. You could do that with In-Case today. You need forensic skills. You require complete documents if you're trying to identify the owner of the hard drive. But an automated approach that you could do is you could just compute a histogram of all the email addresses on the hard drive. Now think about that. If the hard drive was used for email, then the most common email address on that hard drive is going to be the person who was the primary user, because they're in the from and in the to of many, many of the email messages. So I thought, that might work. So the email histogram approach actually works really, really well, and that's how we traced back the majority of the hard drives. It was too hard to look for Word documents Many didn't have Word documents. But when we did the email histogram, the first one at the top was the owner. And here's sanitized from disk number 51. Alice at domain1.com, her email address was on this hard drive 8,000 times. And she was the primary owner. Bob at domain1.com was somebody that she worked with. And domain1.com was actually the name of their company. And then Alice had another account that she also checked. And so we were able to infer that because it was the same username, but different domain. We didn't completely sanitize this. It appears that she was at Stanford Business School. And I could tell that because she's getting emails from their job info network. You can learn a lot about the owner of the hard drive and about the relationships simply by doing the email histogram. And what's really neat about this is you don't need to understand the file system. You don't need to figure out if it's a Macintosh file system or an ext2 or even a FAT or a NTFS file system. It just works. Neat technique. So what I'm doing now is I'm trying to develop a large-scale system for doing this en masse, and I call this approach CrossDrive forensics. Forensics approaches that work across many, many drives at the same time. And the idea is you take in hard drives, you accession them in the field, you image them, and then you put the drives in what I call cold storage. You put them someplace where you won't need to deal with them, but you can recover them if you need them. The drive images go into a image repository. We run feature extractors, which go through that bulk data and capture different features. We throw that into a metadata repository. And then there are correlation agents that you can run over that data to come up with the hot drives. It's a nice architecture. And then you can augment it with information from other sources. So NIST and FBI have databases of hash codes of like known child porn, or there's a list of, say, known application programs. And you can use that to go against the metadata repository for things that you should especially look for or things that you don't have to look for. This gives you a way for rapidly looking over this whole sea of hard drives, and as new drives show up, to incorporate them to run the studies against them all at the same time. Now, what I call Firstorder CrossDrive forensics, I apply this filter to each drive image individually, and I look for images that give the largest response to the kind of filter. And drives that have a lot of response are, by definition, interesting drives. So here I have a filter that looks for CCNs, or credit card numbers. And this is a funny graph, so the scale here is like 0 to 300, and then the scale here is like 300 to 40,000. And over that, say, 200 drive sample, each one of these bars represents the filter's response on a different drive. Red is unique credit card numbers, and blue is then total. So sometimes you see duplicates. So here we have a hard drive with a lot of credit card numbers, and here we have one. Here we have one with a lot. So maybe that's the first one to look at. And if you're like me looking for sanitization failures that are important, then hard drives that have thousands of credit card numbers on them are probably going to be important, because most hard drives just don't have thousands of unique credit card numbers on them. Now, the way that credit card number detector works is there are patterns that make credit card numbers easy to find. So they tend to either be blocks of 16 digits or 4 blocks of 4 digits. They are issued with well-known prefixes corresponding to certain banks. There is something called the credit card number validation algorithm. It's a simple checksum. It's one character. So any random collection of 16 digits has a 1 out of 10 chance of passing. And then it turns out that there are certain numeric patterns that are unlikely in credit card numbers but are very likely in other kinds of bulk data. So this one turns out to be unlikely because it has too many 6s and 7s in it, and there's sort of this progression. Actually, this is from an image file. So a lot of TIFFs and a lot of, for some reason, things that look like credit card numbers show up a lot in various file types. So I wrote this with Flex and in C, and here we are scanning over drive number 105. And there were 3,800 numbers that matched the typographic test. But when we selected out well-known bank prefixes, there were only 90. When we then selected out